Hi everybody, my name is Gabriele Civitarese and I'm a postdoctoral researcher at the University of Milan in Italy. I'm a member of the Everywhere Lab, which is a research lab that works on data management for pervasive and mobile computing. Today, I will talk about our work titled Context-Aware Data Association for Multi-Inhabitant Sensor-Based Activity Recognition. Smart home activity recognition is a research topic that has been deeply studied in the last decades. And today it is still a hot topic. Indeed, continuously monitoring the activities of daily living performed by subjects in their homes enables several healthcare applications, like the early diagnosis of cognitive impairments for the elderly population. Smart home activity recognition is based on the use of unobtrusive environmental sensors that are deployed in the home to continuously track and monitor the interaction of the inhabitant with the surrounding home environment. Smart home activity recognition has been typically tackled with supervised machine learning approaches. However, the majority of works in the literature focused on the assumption that only one subject is living in the home performing activities of daily living alone. Actually, single inhabited settings are realistic because there are several elderly subjects that live alone in their apartments. However, in many cases, there are multiple subjects in the same home, and they may perform the same activity in cooperation. For instance, Bob and Alice can cook together, or individual activities in parallel. For instance, Alice is watching TV while Bob is watering plants. Considering multi-inhabitant activity recognition, a major challenge is called data association. The problem is that environmental sensor events actually cannot identify directly the inhabitants performing activities. Hence, if there are multiple subjects in the same home, how can we correctly associate each environmental sensor event to the inhabitant that actually triggered it? That association is an open problem, very well-known open problem in multi-inhabitant activity recognition. In order to make the data association problem clearer, let's make an example. Suppose that Alice and Bob live together and they are both in the kitchen. Alice is relaxing at the dining table while Bob is cooking. The system recorded two sensor events. The first one is a pressure sensor on the chair that is telling us that someone is sitting at the kitchen chair. We also have a magnetic sensor attached to the fridge door that is telling us that someone is opening the fridge. So the problem of data association here is how can we correctly associate each one of these sensor events to the corresponding inhabitant? So how can the system infer that Bob is actually the one that opened the fridge while Alice is the one sitting on the kitchen chair? This is the overall architecture of our approach. We have environmental sensors, like magnetic sensors to detect opening and closing of doors and drawers, pressure sensors on the chairs to detect when someone is sitting, plug sensors to detect the usage of home appliances, etc. Besides environmental sensors, each subject in the home wears a smartwatch on the wrist. Smartwatches associate the identity to each user, but they also are in charge of collecting inertial sensor data, like accelerometer and gyroscope data, but also positioning data from a micro-localization infrastructure. Our system does not impose a specific micro-localization system. In our experimental setup, we used a Wi-Fi-based micro-localization. Raw sensor data are transmitted to the context aggregation module. This module is in charge of deriving high-level context, like the posture of the user or the location of the user inside the home. Then, raw sensor data and high-level context information are transmitted to the context-aware data association module. This is the core contribution of our work. A knowledge-based reasoning engine analyzes the context of each user to associate environmental sensor events to the users. The output is a personalized stream of sensor data for each inhabitant. Each stream is analyzed by the sensor-based activity recognition which is a single inhabitant activity recognition algorithm. In our architecture, we do not impose a specific technique to recognize activities. In our experiments, we used a deep learning classifier. The activity recognition module outputs a probability distribution over the possible activities. This probability distribution is further refined by the prediction refinement module that uses high-level context data to remove the activities that are unlikely considering the current context. From now on, we will focus our presentation on context-aware data association. That is the main focus of this talk. For each user, we tackle the data association problem using semantic reasoning on the following context data: the user's posture to understand if the user is standing, sitting, or lying; the location of the user inside the home, for example, at the room level. And we also consider the home status, like the semantic position of each environmental sensor and their status, for instance, to understand which sensors are currently activated. Data association is based on an ontology that defines relationships between environmental sensors and context. When a new event is triggered, we use the ontology to compute its context consistency with the context of each user U and the home context. The event is associated with a user U only if context consistent. Let's make an example to make our data association method clearer. Let's continue the previous example to show how our data association method actually works. Suppose that two events occurred, E1 and E2. E1 is the event about the opening of the fridge door, while E2 is the one about the pressure sensor on the kitchen chair. According to Bob's context, he is standing in the kitchen, while Alice is sitting in the kitchen. Thanks to ontological reasoning, we can infer that E1 is context compatible with Bob. He can be standing to open the fridge door that is in the kitchen. On the other hand, E2 is not context compatible with Bob, since he cannot activate a pressure sensor while standing. Similarly, E2 is context compatible with Alice's context, while E1 is not, since she cannot open the fridge while sitting. For the sake of simplicity, we only show the simple reasoning mechanisms, while our ontology encodes more complex relationships and hierarchies to perform consistency checking. In order to evaluate our method, we performed experiments on a dataset that we acquired in our lab. To the best of our knowledge, there exists no publicly available dataset that can be used to evaluate our approach. We involved 12 volunteers that performed 13 different activities of daily living. They simulated different scenarios where up to 4 subjects at the same time performed collaborative and parallel activities. In this plot, we compared our data association mechanism with 2 baselines. The bar on the left is a naive data association method that simply assigns each environmental sensor event to each user. As the plot shows, this method reaches an overall F1 score of 86%. This high value is due to the fact that inertial sensors still help in recognizing activities with a reasonable accuracy. The orange bar on the right is an hypothetical perfect data association approach that perfectly assigns each sensor event to the correct user. The results of our method are shown in the bar in the middle. As it is easy to see, our approach significantly outperforms the naive method, while it is not too distant from the perfect data association strategy. We believe that this is a promising result that highlights the effectiveness of our approach. So, we proposed a novel context-aware data association method for multi-inhabitant activity recognition in smart home environments. And the preliminary results on our dataset show that our approach is effective. We have several directions for future work. First, we want to explore semi-supervised learning in order to reduce the amount of labeled data required to initialize the recognition model. We also want to include more sophisticated context data. For instance, in our experiments, we used room-level microlocalization. We aim to include micro-localization at finer granularity. Finally, we will evaluate our method on larger datasets. Thanks for your attention.